Hello 20-1 students. So today we're looking at moving on with some more in-depth absolute value equations. So in the last lesson we kind of got started with some linear equations and some word problems. Today we're going to move on to working with quadratics. Now a lot of the solution process for this is quite similar to what we've been doing so far, but there's a couple of differences, mostly in how we solve for x. And for today, actually, just because I feel like it'll be easier to understand how we determine the domain, so basically like the acceptable values for x, I feel like it's easier to do that if you see the graph, and then you'll understand the logic behind it. And after that, we can generalize rules to how you'll always be determining your domain. So I'm actually going to skip over that part first, even though in the future you'll probably want to do it first, when you're doing these quadratic equations. Although it's up to you, like obviously on a test, I wouldn't dock marks if you solve for it last either, because regardless of whether or not you've solved for x, the domain remains the same. Okay, so the first thing we're going to do then, because we're skipping past that, is we want to determine the two cases for the absolute value equation and then basically use those to solve for x. So in the first one, we have our standard x squared minus 3x, so like our original equation, and that is equal to 2. For our second case, there's two different approaches you can do. So because our absolute value in here is equal to positive 2, of course, that means that inside of here, if you do these calculations, they could equate to positive 2 or negative 2 inside the absolute value bracket. So there's two different ways that you can solve for the second case. You can either use your original equation and set it equal to negative 2, or you can do what we've been doing where we set this component equal to a negative value and then solve for it. So in the filled in notes, I set my original equation equal to negative 2 for the second case. So if you want to see that way of doing it, you can look at that. But just for consistency, in the worked equation that we do now, I'll follow the same method we've been doing. So I would say we have negative x squared minus 3x, and then that's equal to positive 2. Okay, so let's see. Let's work through the first case here. So we want to basically solve for x, and as we can see when we have a quadratic, we know that basically that means we want to set the whole thing equal to 0 and then factor accordingly. So in this case, we have a positive x squared on this side, so let's move everything to the left side so that stays that way. So x squared minus 3x stays the same. We want this 2 to move over here, and because it's positive, that means we need to subtract it from both sides. X squared minus 3x minus 2 being equal to 2 minus 2 is 0. Then we want to see if we can factor this expression. So we want two numbers that multiply to negative 2 and add to negative 3. There are no numbers like that because we would need a positive and a negative to multiply to the negative 2, which would be 2 and 1. But we would need them both to be negative for them to add to negative 3. So if you don't find easily factorable values that will factor into brackets nicely, then you can look at other methods of solving the quadratic. So for this one, I would consider using the quadratic formula. So we're going to do negative b, so negative of negative 3 is positive 3, plus or minus the square root of b squared, so negative 3 squared is 9, minus 4 times by a, so the coefficient for x is positive 1, times by c, which is negative 2, and that would all be under the square root sign. And then we want to divide that by 2a, so again the a value is that coefficient of 1 in front of the x. When we do that, we end up with 3 plus or minus the root of 17 divided by 2. And so if we do 3 plus the square root of 17 over 2, we end up with x being equal to 3.56. And if we do 3 minus the root of 17 over 2, we end up with x being equal to negative 0.56. Okay, now we don't have our acceptable values set up yet to determine if those work. So we'll do that after we solve case 2 and we make a graph for it. So in this one, I'm going to multiply out my negatives. As you guys know, I like to do the positive one first. So negative times by negative 3x gives us positive 3x. And then negative times by x squared gives us minus x squared. And that's all equal to 2. Now, I don't want to have that negative x squared particularly, so I'm going to move everything over to the right side so it makes my x squared positive. So that means I'm adding x squared to both sides, and positive 3x has to be subtracted, so minus 3x. And so then that's going to end up canceling out those on that side, which add up to 0. And then I'm going to write this in proper order for quadratic. So I have positive x squared, so x squared, minus 3x. And then I had the positive 2 still there, so plus 2. Okay, now I want to see if I can factor that into brackets. Two numbers that multiply to positive 2 and add to negative 3 are going to be 2 and 1, negative 2 and negative 1. Okay, so we're going to have x minus 2, x minus 1. And remember, that's supposed to be equal to 0, so when we solve for x, we're basically looking for values of x inside of these brackets that would make each individual bracket equal to 0, so that when they multiply out, the whole expression is equal to 0. So in this bracket, that means we would need positive 2 minus 2 to make 0, so x would be equal to 2. And in this bracket, that would mean x would be equal to positive 1. Okay, so now we have our solutions that seem appropriate. So what we want to do is graph to verify those solutions, and at the same time we'll figure out how we determine the domain for this equation. All right, so I've made the graph here really quickly. So I went into my graphing calculator, I entered in my absolute value equation and the y equals 2, so from the second part of our equation here. And then if you go to the graph, you can see, oh, actually I might do that a little bit. Y maximum, let's make it 5. That way we can really be zoomed in on it. So here's our graph. And the points that we were interested in were the points where the two different graphs form. So remember that what we have here is the value, like the graph of the original equation and the absolute value one. So we have one parabola that would kind of like extend downwards like this. And then this parabola is a second one that would also kind of extend downwards and mirror this second one here. So basically what we wanted to do to solve for our domain and range is recognize that the point where these two parabolas shift from one to the other is this section here is going to be one parabola, and then both of these sections here are going to be the second parabola. So that means the points on the x-intercept where they cross over are going to be representative of our domain, because one of the equations has to be between here and here. The other equation has to be less than this value and greater than that value. Okay, so when we write our domain for a quadratic equation, we basically set our original expression, so the absolute value of x squared minus 3x is equal to, and then we want to say, is it equal to the original one or the negative one, and for which values of x is that true? So we would say x squared minus 3x if x falls within a certain range, or negative x squared minus 3x if x falls within another certain range. So what we need to do to determine the range is figure out which one of these is the original one. So basically which one of these has the values of x that would satisfy this original equation, and which one has the values that would satisfy the second, the absolute value equation. So let's start out by looking at this one here. So basically what we have here is, let's see, if we want to find a point on the graph, you could go in and find like something easily, like let's say the maximum, right? So we could find the vertex here. So then you would just look for a left bound and then the right bound side, and that will give you your points. So you hit guess. And so the maximum is at 1.5 when y equals negative 2, or sorry, y equals positive 2.25. So x equals 1.5 and y equals 2.25. So basically what we would want to do is go in and see which one of these equations will satisfy that these values. So if we go into just our regular calculations, and it's going to be x squared is 1.5, so 1.5 squared minus 3 times by 1.5 gives us negative 2.25. Okay, so that's following our original equation. If we were to use this one, we would have the negative value of this value, which would be positive 2.25, which is what we see for this component of the graph. So that tells us that this part of the graph has to be representing this second component here, the absolute value. Okay, which means that these components are representing our original equation. So now if we look, the other thing you guys can do here is find your points here where they intersect, right? So we want to know what the coordinates of the graph are at each of these so we can set up our domain, because these ones will be greater than or less than, and these ones will be, this equation will be in between those values. So what I would do here personally is just hit trace and look. You can probably guess, like it looks that like this one's at 1, 2, 3 as an x value. If we do the trace, we go from 2.87 to 3.03, 3.18. So it never lands on the precise value. So if you want to be sure, you just go into calculate, hit value. You want your x value to be 3 because that's your best guess of where this would happen. And if you hit x equals 3, we do find that y equals 0. So we know that that's one of our intersection points. So it'd be 3, 0. For this one, it looks like it's on the origin, but again, we could always trace it. So if we trace, let's see if it lands right on it, which it does. So we have x equals 0 and y equals 0. When we go further past there, we find that we're starting into the next component, like the second version of the equation. So that means 0, 0 is this other point. And so basically what we've learned from this is that this second value, or this second version of the equation, the absolute version, is this middle component, which means that we would say that x has to be greater than 0 but less than 3 because it has to fall in here. So we would say x is less than 3 and greater than 0. Now, just like with the equations we've worked through so far, the absolute value version is always going to be just greater than or less than, not equal to. So that means our original equation would have to be, I'll just fill in my inequalities there. So x has to be less than or equal to, going on this side, would have to be 0. Less than or equal to 0, but it has to be, on this side, going out this way, it has to be greater than or equal to 3. Okay, so those are my two inequalities. So going back to, I mentioned to you guys that I'll give you a generalization for solving these. If you can look at this and see, what do you think is the relationship here between our domain and our equation? Actually, I guess we can just look at this one here. Well, we see that x has to fall always between 0, like 0 is one part, but where does the 3 come from? Well, we have x squared minus 3x. And so with this format, you'll always find that this is going to be true. So your domain will be between those 2 points. So either on the outsides or on the insides. And all you have to do is make sure that you're confirming for which one is it on the outsides and for which one is it on the inside. Okay? Now for all the ones that I've looked at, this middle section is always going to be your negative or your absolute value, and the outside ones are always going to be your original equation. So that can also kind of help you, but I still would recommend, especially on a test, you always do the quick set of calculations to confirm. Now the last thing we want to do is consider our ranges here. So for our original, or sorry, our domain, for our original equation, we said, which was this one, x has to be greater than or equal to 3, which it is here, and less than or equal to 0. And so this is less than or equal to 0. So both of these are valid solutions. We've also confirmed this because if you go into your graph online, you can check the intersection points, and they are at 3.56 and negative 0.56. Then for our absolute value equation, we said that x has to be between 0 and 3, and both 1 and 2 are between those values. So that is also both acceptable solutions. All right. Sorry, that was from the previous lesson. Okay, so you have a chance to try one of those on your own here. X squared minus 13x equals 30. The worked solution is found in the filled in notes, so you can check those to verify your solution. So maybe pause the video and try that one, and then we'll move on to, again, a little bit more of a complex question. Okay, so in this question, we're looking at an absolute value expression that is linear, but it's being set as being equal to a quadratic expression. So because we're always working with the absolute value expression to determine two different cases, because there's the positive and negative, we can kind of go back to our original way of solving these that we looked at in terms of linear equations, where we would start out by determining the acceptable values for each case. So it would be x minus 10 has to be greater than or equal to 0, or it would be, that's case number 1. For case number 2, it would be the negative version of x minus 10 has to be greater than or equal to 0. Okay, so with x minus 10 greater than or equal to 0, we can just add 10 to both sides. So we end up with the statement that x has to be greater than or equal to 10. So that's one of our restrictions. For this one, if we apply the negative times by negative 10 gives us positive 10, times by negative x, or negative times by x gives us minus x. Has to be greater than or equal to 0. So if we add x to both sides, we end up with 10 has to be greater than or equal to x is our other restriction. Now we can go in and start solving our absolute value equations. So this is going to be our second step, is solving. So for case number 1, that means we have x minus 10 is being equal to x squared minus 10x. So again, we want to move everything onto the same side so we can factor it like a quadratic. So let's keep our x squared positive, and let's move this expression over to the right side. So that means if we have positive x, we want to subtract it. If we have negative 10, we want to add it. And same thing to this side. So we'll have negative 10x minus x, and then plus 10 on the other side there. So that's going to give us 0 is equal to x squared minus 10x minus 1x. So negative 10x minus 1x gives us negative 11x. And then we just have the plus 10 at the end. So what we need to find is two numbers that multiply to make positive 10 and add to make negative 11. So that would be negative 10 and negative 1. So we're going to have 0 being equal to x minus 10, x minus 1. And so in order for this to all be equal to 0, we would need each one of these brackets to add up to 0. So x minus 10, so we'd have to have positive 10 to add to 0. So x equals 10. And in this bracket, we would need to have x being equal to 1 for it to subtract to 0. So those are our two for our original equation. For our second, for our absolute value equation, we would have, let's just use this version that we already multiplied out. So 10 minus x is equal to x squared minus 10x. Again, let's keep the positive x, so we want to add, or positive x squared rather, so plus x and minus 10. So over here we'll have plus x minus 10, and so that's going to give us 0 is equal to x squared. Negative 10x plus x gives us negative 9x, and then minus 10. So we need two numbers that multiply to negative 10 and add to negative 9. So that would be negative 10 plus 1. So we'd have 0 is equal to x minus 10 times by x plus 1. And so that means our values for x would have to be positive 10, which we already kind of got there, or negative 1 in this case. So now we want to check these values against our restrictions here. So here we've said that x has to be greater than or equal to 10. So in this case, x is equal to 10, so that satisfies the restriction. So that's a good solution. X is equal to 1, that 1 is not greater than or equal to 10. So this is not a valid solution. We call that our extraneous solution, remember. For this one, 10 has to be greater than or equal to x. So 10 is not, 10 is greater than or, oh, sorry guys, I messed up there. Remember that because this is our absolute value equation, it's not greater than or equal to, it's just greater than. I was wondering why that didn't make sense. Okay, so 10 is just greater than x. And so when we have x being equal to 10, that does not satisfy that because 10 is not greater than 10. So that's an extraneous solution for this absolute value equation. What about negative 1? X has to be, oh sorry, was I saying greater than? Less than, but either way, it's still not appropriate because the value is 10. X has to be less than 10, and in this case, negative 1 is less than 10. So negative 1 is a valid solution. Okay, then we could, so we would say our possible solutions are x equals negative 1 and x equals 10. So remember, those are the x values where we expect these graphs to intersect. So we can go in and graph the two components, right? So the x minus 10 in absolute value brackets, and then the x squared minus 10x. And then we go to our graph. I've already set the window so you didn't have to wait for me to do that. And here we can see our two different graphs. So what we would want to do is check and make sure that these intersection points are where we think they are. So go down to intersect, try and go closer to the intersection point. So first curve, second curve, where are we at here? Y25. There we go. So it says the intersection point is at x equals negative 1, y equals 11, and we said x equals negative 1 would be a solution, so that one seems right. For our next one, we said it'd be x equals 10, so again, we can go to calculate, intersect, and if we go closer over to the intersection here. Oops, sorry guys. There we go. And we get x equals 10. So we've confirmed that those are intersection points, so we know that those are both valid solutions. All right, one more example, just a slightly more complex quadratic, and then we'll be finished for the day. Now with this one, I would recommend what you might want to do is try it yourself first, because the solution process should be the same as what we've been doing, like what we just did for the last question. So this would be a good one for you to try on your own. So if you want, you can pause the video here and then come back and watch the worked solution if you need it. Okay. Yeah, so let's go through it. The first step is determining our acceptable values for our absolute value. So in case number 1, we just have x minus 5. It has to be greater than or equal to 0. And so that would be x has to be greater than or equal to 5. For our second case, for our absolute value version, it's going to be negative x minus 5. Has to be equal to, or sorry, has to be greater than 0. Let's not make that same mistake again. Greater than 0. And so multiplying that out, we end up with 5 minus x has to be greater than 0. So we can add x to both sides, so 5 has to be greater than x. Okay, so these are our two restrictions for each case. Now we can go in and try to solve each case. So this is our second step. So for case 1, it's going to be x minus 5 is equal to x squared minus 8x plus 15. We want to keep our positive x squared, so let's go minus x plus 5 from both sides, minus x plus 5. And so that's going to add up to 0 is equal to x squared. Negative 8x minus x gives us minus 9x. And 15 plus 5 gives us plus 20. If we want to factor that, we need numbers that multiply to positive 20 and add to negative 9. So that would be 5 and 4, and they have to both be negative. So we'd say 0 is equal to x minus 5, x minus 4. And so our values for x then would be positive 5 here and positive 4 here. If we check it against our restriction, it says x has to be greater than or equal to 5. So if x is equal to 5, that one is good. But 4 is not greater than or equal to 5, so this would be an extraneous solution. Okay. Going through this solution, we would have 5 minus x is our absolute value version, has to be equal to x squared minus 8x plus 15. Okay, and then let's move this over. So we would have minus 5 plus x to both sides, so plus x minus 5. So that's going to add up to 0 is equal to x squared. Negative 8x plus x gives us minus 7x. Minus 7x, and then positive 15 minus 5 gives us plus 10. So two numbers that multiply to 10 and add to negative 7 would be negative 5 and negative 2. So we're going to have x minus 5, x minus 2. And that means our possible values for x would be plus 5 or plus 2. Now, checking these against our restriction, 5 has to be less than 5, which that's not true. That's an extraneous solution. 2 has to be less than 5, which it is, so that's a valid solution. Okay, so those are our two solutions. It looks like x equals 5 and x equals 2. So keep in mind those are the points where we expect to see intersection. Now I'm going to walk you guys through a different way to verify instead of graphing. So just one kind of thing you can fall back on if you don't love the graphing. So if we verify, we can verify by substitution. Okay, so basically that means we would take each of these values, substitute them into the original equation, and determine whether they're accurate. So for x equals 5, we would do absolute value 5 minus 5 is equal to x squared, so 5 squared is 25, minus 8 times 5 is 40, so minus 40, plus 15. 5 minus 5 is 0. 25 minus 40 gives us negative 15 plus 15, which is equal to 0. So we've verified that that's an appropriate solution. And then we can do the same thing for 2. So 2 minus 5 as an absolute value is equal to 2 squared, which is 4, minus 8 times 2 is 16, plus 15. So 2 minus 5 gives us negative 3. Oops, getting off the page a little bit there. And now my negative is in a funny spot there. Okay, so negative 3 is equal to 4 minus 16 is negative 12 plus 15. And the absolute value of negative 3 is 3. Negative 12 plus 15 is 3. So again, we've verified our solution. Okay. So you could go through and do that for all of these. Personally, I prefer graphing, but sometimes it's nice to have a different method to fall back on if you feel more comfortable with that. The only thing is, of course, if you were doing like this on a test, you would also want to go through and verify your extraneous values. So go through and try 4 as well. And then for this one, well, sorry, no, actually you wouldn't have to go through and verify your extraneous ones because they're invalidated by our restrictions. So actually, no, you would only have to verify the correct solutions. Okay, so you have an assignment out of the textbook, and that is everything for this section. And next time we'll be in our last lesson of the chapter, which is looking at reciprocal linear functions. So I will see you then.